Hello, and welcome to our lesson on relating algebra and functions to real-life problems. In this lesson, we will jump straight in with real-life problems to apply what we have learnt throughout our lessons on functions. We will use core algebraic ideas we've covered, including functions and expanding and factorising brackets. We'll go through all the necessary steps, but feel free to go back and familiarise yourself with these if needed. Imagine you are planning a school event and need to optimize the costs for maximum efficiency. Using functions, you could model the expected turnout and expenses, and by expanding and factorizing, you can solve for the best financial plan. Let's dive straight into some other examples of real-world problems. We'll start with a practical example involving population growth in chickens. Suppose the increase in chickens in a certain area is described by the function f of x equals x squared plus 2x plus 1, where x is time in years. To plot this function, we first need to calculate some points. Choose some values of x such as x equals 1, 2, and 3, and compute the corresponding y values. For x equals 1, we get 1 squared plus 2 times 1 plus 1, which gives 4. For x equals 2, we get 2 squared plus 2 times 2 plus 1, which gives 9. For x equals 3, we have 3 squared plus 2 times 3 plus 1, so we get 16. So we can plot these points on a coordinate grid and draw a curve that fits them. This function tells us how many chickens there will be after x number of years. Let's look at a financial example involving the cost of energy over time, using a linear function y equals ax plus b. Assume we have data points that show how energy costs have changed over several years. For instance, x could be years and y could be the cost. If we have data for years 1, 2, and 3 with corresponding costs of 3, 5, 7, these suggest a linear relationship because the cost of energy has increased by 2 each year. We can now plot these points and draw a graph to show this relationship. From the graph, the slope, A, represents the rate at which energy costs increase annually. We can see that the slope is 2, which represents the annual energy cost increasing by 2 each year. The y-intercept B tells us the base cost of energy when x equals 0. In this case, it is 1, and it can be interpreted as the current fixed charge of using energy. So this is what you pay before any usage is factored in. Putting these two findings together, we can write the function as y equals 2x plus 1. We can also use the graph's slope and intercept to predict future costs. We can see that for every year, the cost goes up by 2 units because the slope is 2, so we can use this to predict the cost in future years. As we can see, these mathematical models and functions help us make sense of real-world problems, whether we are observing animal populations or managing finances. Now let's move on to a word problem. Imagine you've decided to start a lawn mowing business over the summer and you want to figure out how much you could earn. To do this, we can use functions. Firstly, let's define our variables. We will denote x as the number of lawns you mow and y as the amount of money you earn. Now imagine the cost for mowing one lawn is set at a constant rate of £10. Essentially, that will mean for each lawn you mow, you earn £10. This kind of relationship can be exactly expressed by a linear function of the form y equals mx plus c, where m is the gradient, x is the input variable, and c is the constant. We can think about some points on our graph. If you mow one lawn, you get £10. If you mow 2 lawns, you get £20. If you mow 3 lawns, you get £30, and so on. Plotting these points on the graph, we see this linear relationship. The slope here is 10, so the value of m is 10. The y-intercept is 0, so c is 0. Substituting this back into our linear function, we get y equals 10x. So if you mow 5 lawns, the equation becomes y equals 10 times 5 and you earn £50. The function directly maps the number of lawns to the earnings. So in essence, the more lawns you mow, the more money you earn. This real-life scenario illustrates the practicality of understanding and using functions along with other algebraic techniques in day-to-day problem solving. In today's lesson, we explored how algebraic functions can be applied to solve real-life problems, enhancing our understanding and practical use of algebra. We looked at practical examples involving population growth in chickens, using a quadratic function to plot the graph and interpret the rate of population increase. Overall, the past lessons on functions and algebra should have given you a solid foundation to tackle more complex problems to come. Make sure to come back and review these in the future to consolidate what we have learned. Watch the rest of the GCSE Maths course at Sophos Education.